Good evening, everyone. So, in the previous class, we had discussed about different types of relations. I hope you had remember all the different types of relations. The main relations are reflexive relation, symmetric relation, and transitive relation. A reflexive relation means suppose a relation is defined on a set A, then a relation is always a subset of A cross A that we have to remember. So the elements of the relation will be of the ordered pair A comma B, where this A belongs to the first set and B belongs to the second set. So, if a relation is defined on a set capital A and the relation is said to be reflexive if every element of that particular set small a is related to itself. That means for every a must be related to itself. So that should be there. This is for every a. Then the relation is said to be a reflexive relation. Then for symmetric and transitive, it is if condition. That is in symmetric, if AB. If ordered pair AB belongs to R, then BA must be there. Where this A comma B belongs to set A. The relation is defined on a set A. If AB belongs to R, then BA must be there. In the same way, we can define transitive relation. Transitive relation means if AB comma BC, if these two ordered pair belongs to R, then AC must be there. So these are the three conditions. So this is the condition for reflexive, this is for symmetric, and this is for transitive. Okay. So if a relation satisfies these three conditions, that is, if the relation is reflexive, if the relation is symmetric, if the relation is transitive, then that relation is said to be an equivalence relation. So today in this class we'll discuss some examples of equivalence relation and some examples we have to check whether the given relation is an equivalence relation or not. Okay. So first we'll consider a relation. The relation R, it is defined on a set of all lines in a plane. That is, the relation R is defined on a set L. This L is nothing but the set of all lines in a plane. So this is the set. So the relation R is defined on L. R is defined on L in such a way that this R is defined as set of all ordered pair A comma B, where AB belongs to L and A is parallel to B. Okay. So this is the relation, and we have to check whether this relation is an equivalence relation. So the first thing we have to check is whether this relation is an equivalence relation. For that, we have to check three conditions. For that, first you have to check whether it is reflexive, then you have to check whether it is symmetric, and if it is transitive. If all the three conditions are satisfied, then only we can say that the given relation is an equivalence relation. So one by one we will check. So for that, first you have to understand what is the relation and where it is defined. These two things you have to remember first. So the relation is defined on a set of all lines in a plane. It is defined on L. L contains all the lines in a plane. And the relation is defined as AB, where this A and B both are lines actually. It belongs to L and A is parallel to B. So, what is a parallel line that you have to understand? Parallel lines means the parallel lines never intersect each other and their distance between two parallel lines will be always equal. So, these two things you have to remember. So, for that, first you have to check whether it is reflexive. So, by definition, we know that if a relation is reflexive, every element must be related to itself. So, here, what is the element here? Here, suppose you take A, means that A is a line actually. So, this A belongs to R means what is the condition here? The condition is if AB belongs to R, A is parallel to B. So if A belongs to R, then what should be true? A parallel to A. If A parallel to A, then only A belongs to R. And we know that every line is parallel to itself, or every line is parallel to itself. Suppose if you draw a line, that line is parallel to the same line. So we can conclude that AA belongs to R for every A belongs to L. So this relation is, this R is reflexive. So this R is reflexive because we can use the property of parallelism. That is, a line is parallel to itself. So using that, we can say that this relation is reflexive. Then next you have to check whether it is symmetric. For if it is symmetric, so if you take here in this case in reflexive, if you take any line is parallel to itself. For every line, the line is parallel to itself, so it is reflexive. Then for symmetric relation, the condition is that if AB belongs to R, then we have to prove that BA must be in R. If AB is there, then BA should be there. So suppose that if AB belongs to R, then what is the condition using this given relation? If AB belongs to R, then A is parallel to B. This is true. And we know that if AB parallel to A is parallel to B, a line A is parallel to B, then clearly B is parallel to A. That means BA belongs to, if AB is there, then BA is there. That means it is symmetric. So using parallelism, that is, we are assuming that AB belongs to R. If AB belongs to R, what is the condition? A is parallel to B. A is parallel to B. So if A is parallel to B, if two lines are parallel, suppose this is A and this line is B. These two lines are parallel means clearly what will happen? B is parallel to A. So we can conclude that BA belongs to R. So if AB belongs to R, then BA belongs to R. So it is continuous. So the function in this relation is symmetric relation. Okay. So this relation, so this R ordered pair AB such that AB belongs to L, A is parallel to B. This relation is symmetric as well as reflexive. Next, you have to check whether it is transitive. If it is transitive, what is the condition? Condition of transitivity, you have to remember the condition of transitivity is that if AB comma BC belongs to R, then AC should be there. So if AB and BC belongs to R, then AC must be in that relation. That is the condition. So what we have to do is first you assume that AB belongs to R. If AB belongs to R, then what is the condition? A is parallel to B. Okay, then BC belongs to R means B is parallel to C. So two lines, A is parallel to B. This is a line A. It is parallel to B, and this line B is parallel to another line C. Then we can say that clearly A and C, they are parallel. So if AB BC belongs to R, then that clearly implies that AC belongs to, that is, this one A parallel to B parallel to C clearly implies A parallel to C, which implies AC belongs to. So this relation is transitive. So using the given set and using the given relation, you have to check whether the given relation is an equivalence relation. For that, first you have to check whether it is reflexive relation, whether it is symmetric, and it is transitive. So these three things you have to remember. If all the three are true, then only we can say that it is an equivalence relation. So here the set is it is defined. The set is the lines of planes, lines in a plane. That is the set of all lines in a plane. That is the given set. In that set, the relation is defined as set of all ordered pair AB such that AB belongs to L. That is A and B both are lines, and A is parallel to B. That means if A is parallel to B, then only it belongs to the relation. So first we have to check that which is this relation, whether it is reflexive. We know that every line is parallel to itself, so it is reflexive. Then if a line A is parallel to B, then clearly B is parallel to A, so it is symmetric. Then transitive relation, if a line A is parallel to B, then B is parallel to C, then clearly the line A is parallel to C. That means AB belongs to R, BC belongs to R, clearly implies AC belongs to R. So we can conclude that this relation is an equivalence relation. That means the relation defined on a set of all lines in a planes in a such a way that R equal to set of all ordered pair AB such that A and B belongs to L where A is parallel to B. It is an equivalence relation. Okay. Then the same way, one more example we can see, that is the relation is defined on a same set, that is L, the set of all lines in a plane, the same set only, it is defined on L, lines in a plane, but the relation is a bit different. That is, it is defined as ordered pair AB such that A comma B belongs to L if A is perpendicular to B. A perpendicular to B. Okay, we have to check whether it's an equivalence relation. So if it is an equivalence relation, it is reflexive, symmetric and transitive. So these three relations we have to check for this particular relation. So first we will check whether it is reflexive. So reflexive means AA must be there. If AA must be there means A is perpendicular to A, then only it belongs to R. Every line is perpendicular to itself. It is not true. Every line is perpendicular to itself means if two lines are perpendicular, what is the condition? This is A and this is B. These two lines are perpendicular. The angle between the two lines must be 90 degree. So every line is not perpendicular to itself. So clearly we can say that it is not reflexive because every line is not perpendicular. This is not true. A perpendicular to A is not true. Okay, so it is not reflexive. The relation is not reflexive. Next, we will check whether it is symmetric. So, from this we can conclude it's not an equivalence relation, but sometimes the question will come, check whether it is symmetric or check whether it is transitive. Like that also questions will come. So, we'll discuss all the three relations, whether it is true. So, next we will check whether it is symmetric. So, symmetric relation means if AB belongs to R, suppose we are assuming that AB belongs to R. If AB belongs to R means A perpendicular to B. This is true. A line A is perpendicular to B. So if a line perpendicular to A is perpendicular to B, which implies B is perpendicular to A. The otherwise also it is true because here you can see that this is a line A, this is a line B. Two lines are given. So A is perpendicular to B means B is also perpendicular to A. And we can say that BA belongs to R. So the relation R is symmetric. So this relation is symmetric. Okay, so the condition is that A perpendicular to B implies B perpendicular to A. That is AB belongs to R implies BA belongs to R. So the relation is symmetric. Next, third one, we have to check whether it is transitive. Okay. So transitive relation, we have to check. So transitive means we have to check if AB comma BC belongs to R, which implies AC belongs to R. So this must be true. If AB and BC belongs to R, then clearly AC must be there. So we are assuming that AB and BC are there. That means A is perpendicular to B, A perpendicular to B and B perpendicular to C. These two conditions are true. A line A is perpendicular to B, B is perpendicular to C. Next you have to see whether A is perpendicular to C. Then only AC belongs to R. If AC belongs to R means A must be perpendicular to C. Okay. So if A is perpendicular to B, roughly I am drawing something that is suppose this is the line A, this is the line B. Okay. So this is A, this is B. Two lines. Here A and B are perpendicular And I am drawing another line C which is perpendicular to B. So here all these conditions are true. That is, the line A is perpendicular to B. So AB is there. Then the line B is perpendicular to C. BC is there. But what can you say about A and C? They are not perpendicular. Now what will happen is A and C are parallel. So if AB belongs to R, BC belongs to R, does not imply that AC belongs to R. That is, AB belongs to R, BC belongs to R means A is perpendicular to B, B is perpendicular to C, but A is not perpendicular to C. A is parallel to C. Line A is parallel to C. That means AC does not belongs to R. So this relation is not transitive. So we can conclude that this relation R defined on the set of all lines in a plane such that ordered pair AB such that AB belongs to L and A perpendicular to B is not a reflexive relation. It is not a reflexive relation. It is a symmetric relation, but it is not a transitive relation. That is, we can conclude that it is a symmetric, but neither reflexive nor transitive. So these things you have to remember. Why it is not reflexive? Because every line is not perpendicular to itself. Every line is not perpendicular to, because if it is reflexive means a should be there, every element must be related to itself. Here the relation is perpendicularity, but every line is not perpendicular to itself, so it is not reflexive. But it is symmetric. Symmetric means if a line A is perpendicular to B, then clearly B is perpendicular to A, so the line is, the it is symmetric, the relation is symmetric. But for transitivity, we can assume that AB, BC belongs to R. AB belongs to R means A is perpendicular to B and B is perpendicular to C. But what will happen? A and C, they are not perpendicular. Actually, A and C are parallel. Okay, so we can conclude that AB, BC belongs to R, but AC does not belong to R, because if AC belongs to R means A must be perpendicular to C. That is not happening here. Okay, so this relation is neither reflexive nor transitive, but it is symmetric. The first case we discussed the same line L, same set we discussed, that is L, the lines in a plane defined as R equal to set of all ordered pair AB such that AB belongs to L, A parallel to B. That is an equivalence relation. A parallel to B is an equivalence relation, but A perpendicular to B is not an equivalence relation. It is because it is neither reflexive nor symmetric. Okay, so the first one is an is a example of an equivalence relation, but the second one is not an equivalence relation. Okay, so in the next class we will discuss some more questions related to equivalence relation. Thank you.